Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 11.5 Part 1 homework solutions on recursive sequences. For the first few problems, they want us to write the first 6 terms of the sequences that are given. So in this one, we have the base case 1, so that'll actually be our first term. We get that one for free. And then for finding the rest of them, we need to take the previous term and just add 3 to it. So for A2, we need A1 plus 3, that's 1 plus 3, or 4. For A3, that's A2 plus 3, so 4 plus 3, which is 7. A sub 4 is going to be A sub 3 plus 3, so that's going to be 7 plus 3, or 10. A5, we've got A4 plus 3, that's going to be 10 plus 3, so 13. And then finally, A sub 6, that's going to be A sub 5 plus 3, so 13 plus 3 giving us 16. To write the first 6 terms of this sequence, let's start with the first term, which is this f of 0 equals 4 term. And then to find the rest of them, we have to take the previous term and multiply it by 2, according to this recursive rule. So for f of 1, we've got 2 times f of 0, 2 times 4, and that's going to be 8. F of 2 is 2 times f of 1, so 2 times 8, which is 16. F of 3 is 2 times f of 2, so 2 times 16, giving us 32. F of 4, we've got 2 times f of 3, that's 2 times 32, which is 64. And then finally, f of 5 is going to be 2 times f of 4, 2 times 64, which is 128. For this problem, to get the first 6 terms of this sequence, let's start by writing the first term, which is 2. And then for each of the next few terms, we have to take the previous term, square it, and then add 1. So a sub 2 is going to be a1 squared plus 1. That's 2 squared plus 1. This is 4 plus 1, which is 5. For a sub 3, that's going to be a2 squared plus 1. So 5 squared plus 1. That's going to be 25 plus 1, so 26. And here's where we're going to start using the calculator. So for a sub 4, we need a sub 3 squared plus 1. So 26 squared plus 1. And then let me go to Desmos for this. So 26 squared plus 1 is going to be 677. Next up, a sub 5, we've got a sub 4 squared plus 1, so 677 squared plus 1. 677, square that, add 1, comes out to 458,330 even there. And then finally, a sub 6, we've got a sub 5 squared plus 1, so this is ridiculous. It's this huge number, square that, and add that little 1 at the end. So let me just do answer squared and then add 1. And then that comes out to about 2.101, if you want to round it off, times 10 to the 11. We'll take their word for it. For this problem, we're trying to find the first 6 terms of this sequence. So good news, bad news, or at least other news. Good news is they've given us the first 2 terms. F of 0 is 2, f of 1 is 4. So we've already got 2 for free. The other news is that the rule requires us to use both of the previous terms. So a little bit more work on the plugging in end. So if I basically have to do the last term minus the second to last term. So to find f of 2, for example, I need to do f of 1 minus f of 2 minus 2, f of 0. So that's 4 minus 2, which is 2. And now let's do the rest of them. F of 3, that's going to be f of 2 minus f of 1. So 2 minus 4, which is negative 2. F of 4 is f of 3 minus f of 2. So that's going to be negative 2 minus another 2, which comes out to negative 4. And the last term I need to find, f of 5, that's f of 4 minus f of 3. So that's negative 4 minus negative 2, so plus 2, which comes out to negative 2. For this problem, they want a recursive rule for this sequence. So let's check first to see if it's one of our regular sequences, arithmetic or geometric. So we've got 21 and 14 minus that is negative 7. 7 minus 14 is also negative 7. I keep subtracting 7 each time, so this is an arithmetic sequence, which means I can use my recursive style of arithmetic, which is a sub n minus 1 plus the common difference, plus d. So let me write out my a1. That's going to be 21. That's part of my recursive definition here. And then for the recursive part of the recursive definition, we're going to do a sub n minus 1 plus the common difference of negative 7, so minus 7. To get a recursive rule for this sequence, let's first check to see if it's one of the more common ones. So we don't have a common difference. This is adding 9 and then adding 36, so definitely not a difference there. Am I multiplying by the same thing each time? 3 times, so let's see, 12 divided by 3 is 4. 48 divided by 12 is also 4. And 192, I'll bet that's also 4 if I divide that by 48. So it looks like this is a geometric sequence. So my geometric recursive formula, we've got r times a sub n minus 1. So the a1 in this case is 3. And for the r value, if I just do 12 divided by 3, that's going to be 4. So I can just write the recursive part as a sub n equals 4 times a sub n minus 1. On this problem, to write a recursive rule, let me first check the most common ones. So let's see, do I have an arithmetic series? Well, 2 plus 3 is 5, but 5 plus 3 is not 10, so that doesn't work. How about geometric? 5 divided by 2 is 2.5. 10 divided by 5 is 2, so it's not geometric, no common ratio. Next, am I doing something with 2 terms to get the next term? Well, 2 times 5 is 10. 5 times 10 is 50. And 10 times 50 is 500, so it looks like that's what's going on, is we're taking the prior 2 terms and multiplying them together. Because I use 2 terms at once, a recursive rule for this is going to require 2 base cases. So I need to spell out a1 equals 2 and a2 equals 5. That's the starting point for this. And then to get a sub n, I just need to do a sub n minus 2 times a sub n minus 1. So second to last term minus last term. We're trying to write a recursive rule for this one. So let's go through our usual list of suspects. Is this arithmetic? Well, negative 2, or negative 1 rather, minus negative 3, that's plus 3, that's a difference of 2. 2 plus 1 is 3. 6 minus 2 is going to be 4. So although I kind of see a pattern, because 11 minus 6 is 5, it's not a true arithmetic series, but there's some kind of addition, progressively greater addition going on. So that's one thing I at least notice with that pattern. In terms of multiplying, 1 over 3 is 1/3. 2 over 1, that's going to be negative 2 there. This is definitely not a geometric series. Am I doing things with 2 terms to get the next term? Well, if I added these together, or if I subtracted rather, negative 1 minus negative 3 would give me 2, but 2 minus negative 1 is not 6, so that pattern doesn't hold. Is there anything I'm doing with the index number to get the next term? Well, let me think here. Negative 1, that's the second index, and negative 3, is there something I could do with a negative 3 and a 1 or a 2 to get this negative 1? Well, negative 3 plus 2 would give me negative 1. Okay. So what might have happened here is maybe I used the last term and the index of the term that I wanted to get this. I mean, it worked this first time. Let's see if it works on the next one. So if I want to get 2, I would have to take my last term of 1, negative 1, and add the index 3. Negative 1 plus 3 does give me 2. Okay. 6. I would get that by doing the last term 2 plus the index 4, and that is 6. And 11 is indeed the last term plus the index 5. So my A1 is going to be negative 3. And then for the pattern here, I'm doing last term plus current index. So A sub n minus 1 plus n. And that'll do it. For this problem, I'm trying to write a recursive rule for the sequence here. Is it arithmetic? Well, 4 minus 1 is 3. 5 minus 4 is 1, so not arithmetic, no common difference. Is it geometric? 4 divided by 1 is 4. 5 divided by 4 is not 4, so not geometric. Can I do something with two previous terms to get the next term? 1 plus 4 would be 5. 4 plus 5 is 9. 5 plus 9 is 14. So this looks kind of like a Fibonacci sort of sequence here. So I need two base cases then. A sub 1 equals 1 and A sub 2 equals 4. And then for my rule, I just have to do A sub n minus 2 plus A sub n minus 1. Just add the previous two terms together, and that gives me each term.